Welcome back. So far, we've learned how AI thinks and what it's made of. Now we follow the journey, the full life cycle of an AI system, from the moment raw data is collected to the day the model is respectfully retired. Why does this matter? Because in the AAIA world, most audit findings live at specific life cycle stages, and knowing the map means knowing where to dig. Here's our route through this chapter in a handful of focus areas. First, the data stage: collection, source assessment, pre-processing, and the quietly dangerous art of feature engineering. Think of it as inspecting the ingredients before anyone starts cooking. Second, the build stage: splitting data correctly, selecting algorithms, tuning hyperparameters, and validating in ways that prevent leakage, one of the sneakiest failures in machine learning. Third, the launch stage: deployment patterns with wonderful names like Shadow, Canary, and Blue-Green, plus the difference between batch and real-time inference and the MLOps pipelines that hold it all together. And finally, the living years: monitoring for drift, deciding when to retrain, and eventually decommissioning the model without losing institutional knowledge. By the end, you'll see an AI system the way a physician sees a patient, as something with a birth, a life, checkups, and an eventual farewell. If you're preparing seriously for the AAIA, this chapter is pure exam territory. So subscribe, settle in, and let's begin the journey. Every AI system begins the same way, with data being collected. And here's a truth I want you to tattoo on your audit brain. Most AI failures are data failures wearing a model costume. So let's start where the trouble starts. Data collection sounds mundane, but ask yourself, where does this data actually come from? Internal systems, purchase data sets, web scraping, user uploads, third-party brokers? Each source carries different questions. When I reviewed a marketing AI for a client, we discovered a chunk of their training data came from a purchased list whose original consent covered newsletters, not AI profiling. Legally shaky, ethically worse, and nobody had checked because the data just arrived. That's why source assessment matters. For every source, an auditor asks three things. Do we have the legal right to use this data for this purpose? Is the source credible and current? And does the data actually represent the population we'll make decisions about? A credit model trained mostly on urban salaried customers will stumble badly on rural gig workers. Same country, different world. Then comes pre-processing, the cleanup. Raw data is messy: missing values, duplicate records, inconsistent formats, ages recorded as 150. Teams fix these through cleaning rules. But listen carefully, every cleaning decision is a judgment call. Deleting incomplete records might quietly delete an entire demographic that fills forms differently. Replacing missing incomes with the average smooths the data and buries reality. So request the pre-processing documentation. If the answer is what documentation, you found your first finding before ever touching the model. Let's talk about a step most people outside data science have never heard of, yet it shapes every AI decision: feature engineering. This is where humans decide which signals the model gets to see, and it's one of the most consequential, least audited corners of the life cycle. A feature is simply an input the model uses. Raw data might contain a customer's transaction history. A data scientist engineers features from it: average monthly spend, number of late payments, ratio of credit used to credit available. These crafted signals are what the model actually learns from. It's like a chef deciding which ingredients even enter the kitchen. The recipe can only work with what's on the counter. Now, where's the risk? First, proxy variables. Suppose a model isn't allowed to use religion or caste, so those columns are removed. Fine. But PIN code remains. And in many cities, PIN code correlates strongly with community. The model learns the forbidden pattern anyway through the back door. The famous Amazon recruiting tool did exactly this. It learned that words on resumes associated with women predicted rejection because history had. Nobody programmed discrimination. The features carried it in. Second, leakage through features. Someone once included days since account flagged as a feature in a fraud model. Brilliant accuracy in testing because the feature only existed after fraud was found. In production, useless. So what do you ask? Show me the feature list. Who approved it? Which features were tested for correlation with protected attributes? A model is a mirror of its features. Audit the mirror before judging the reflection. Here's a question that sounds academic, but decides whether performance numbers can be trusted at all. When the team built this model, how did they split their data? Let me explain why this little detail deserves your full attention. Machine learning has a golden rule. You must evaluate a model on data it has never seen. So teams split their data set into three parts. The training set, where the model learns. The validation set, used along the way to tune settings and compare candidate models. And the test set, locked away like a sealed exam paper, used exactly once at the end to measure true performance. Think of it like coaching a student. Training data is the textbook. Validation is the weekly mock tests that guide your teaching. And the test set is the board exam, unseen, final, honest. Now imagine a coaching center that lets students peek at the board exam paper during preparation. Their results would look spectacular and mean nothing. That peeking is exactly what happens when data splitting goes wrong. And it goes wrong in subtle ways. If the same customer appears in both training and test sets, the model has effectively seen the exam. If data is split randomly when it should be split by time, the model trains on the future and predicts the past. Impossible in real life, flattering in reports. I've watched a forecasting model lose 15 points of accuracy the moment we redid the split by time. The original number wasn't a lie, it was an illusion. Your audit task is simple. Show me how the split was done and prove the test set stayed untouched. Trust the process before you trust the score. Now we arrive at the stage everyone imagines when they hear AI, actually building the model. But here's the insider secret. This stage is less about coding genius and more about a series of documented or sadly undocumented choices. And choices are exactly what auditors audit. First choice, algorithm selection. Should this problem use a simple logistic regression, a random forest, or a deep neural network? Remember our accuracy versus explainability trade-off from Chapter 1? This is where it gets decided. Here's what I look for. Evidence that simpler options were considered. If a team jumped straight to a complex black box for a regulated decision like lending, I want to see the justification. Sometimes the honest answer is the data scientist wanted to try something cool. That's fine for a hackathon, not for credit decisions. Second, the experimentation process. Model building is iterative. Try, measure, adjust, repeat, sometimes hundreds of times. Mature teams use experiment tracking tools that log every run, its settings, and its results. Immature teams keep it in someone's head or a laptop folder called final_model_v7_really_final. You can smell the difference in 5 minutes. Third, hyperparameter tuning. Remember, these are the human-chosen dials, learning rate, tree depth, and so on. Tuning them is legitimate and necessary, but excessive tuning against the validation set is like a student rehearsing only mock tests until scores look great. Another quiet path to overfitting. Your questions then, why this algorithm? Where are the experiment logs? Who reviewed the final choice? If the building was sound, the paperwork exists. If the paperwork doesn't exist, was the building sound? Let's now put the model on trial before it touches real customers. This stage is validation, and for auditors, it's home turf, because validation is essentially the evidence-gathering phase of the AI lifecycle. Good teams go beyond a single test score. They use techniques like cross-validation, where data is rotated through multiple trained test splits to make sure performance isn't a lucky accident of one particular split. Think of examining a student with 5 different question papers instead of 1. Consistent scores across all 5? Now you believe the grade. Next, the silent killer, Data leakage. Leakage means information from the future or from the answer itself sneaks into training. We saw a flavor of it with features, but it hides everywhere. A hospital readmission model once included the discharge medication list, which doctors only finalize after deciding the patient's condition. The model looked psychic in testing and collapsed in production. So ask directly, what leakage checks were performed? A blank stare is an answer too. Then comes my favorite word in this whole lesson, reproducibility. Can the team rebuild the same model from the same data and code today and get the same results? This is the AI equivalent of an accounting audit trail. It requires versioned data, versioned code, recorded settings, and fixed random seeds. When a regulator asks next year why the model denied someone's claim, we can't recreate it is not an acceptable sentence. So here's your checklist mindset. Varied validation, documented leakage checks, and a reproducible build. Miss any one, and every performance number downstream is standing on sand. The model has passed validation. Time to release it into the wild. But how you release an AI model matters enormously. And thankfully, engineers have developed some wonderfully named patterns for doing it safely. Let's decode them because the AAIA exam expects you to know each one. First, shadow deployment. The new model runs alongside the old system, seeing real traffic and making real predictions, but its outputs go nowhere. It's a silent understudy watching from the wings. Teams compare its decisions to the current systems without any customer ever being affected. Zero risk, pure learning. If a client skipped shadow mode for a high-stakes model, ask why. Second, canary deployment. Named after the canary in the coal mine. The new model serves a tiny slice of traffic, say 5%, while everyone else stays on the old one. If the canary struggles, errors spike or complaints rise, you pull back instantly, having harmed almost no one. Third, blue-green deployment. Two identical environments exist, blue running the old version, green running the new. You switch traffic from blue to green in one move, and crucially, blue stays warm. If green misbehaves, you flip back in minutes. Think of it as changing planes at the gate while keeping the first plane fueled. And fourth, A/B testing, where two versions run simultaneously for different user groups and you measure which performs better on business outcomes. The audit angle? Each pattern is a control against deployment risk. So ask, which pattern was used, what were the rollback criteria, and who had authority to pull the trigger? Launching straight to 100% of users with no rollback plan? That's not confidence. That's a finding. Let's clear up a distinction that shapes cost, risk, and monitoring for every deployed model. Does it think in batches or in real time? The technical word for a model making predictions is inference, and how inference happens changes what you audit. Batch inference is the overnight worker. Once a day or once a week, the model processes a big pile of records at once. Think of a bank scoring its entire customer base for churn risk every Sunday night. If something breaks, there's time to catch it before Monday. Errors are contained, review is possible, life is calmer. Real-time inference is the air traffic controller. A request arrives and the model must answer in milliseconds. Card fraud checks at the moment of payment. Chatbot replies. Dynamic pricing. Here, there's no human between prediction and consequence. Speed is the feature and speed is the risk. If the model degrades at 2 a.m., it makes thousands of bad calls before anyone's coffee is poured. So for real-time systems, your audit lens shifts heavily toward automated monitoring, alerting, and failover behavior. What happens if the model doesn't respond in time? Does the transaction go through, get blocked, or fall to a rules-based backup? Someone made that choice. Find the document. Holding all this together is MLOps, machine learning operations, the assembly line that moves models from laptop to production repeatably. Automated testing, versioning, approval gates, deployment scripts, monitoring hooks. Think of MLOps as internal controls made executable. A mature pipeline means changes follow a governed path. An immature one means a data scientist can push to production on a Friday evening. You already know which organization you'd rather audit. Here's the uncomfortable truth about deployed AI. The day a model goes live is the day it starts dying. Not because the code changes, but because the world does. This lesson is about watching the machine, and it's one of the highest value areas in any AI audit. The villain here is called drift. Data drift means the inputs arriving today no longer look like the training data. Imagine a credit model trained before the pandemic, suddenly seeing lockdown-era spending patterns. Same model, alien world. Concept drift is deeper. The relationship between inputs and outcomes itself changes. Fraudsters adapt their tactics, customer behavior evolves, and yesterday's signals stop meaning what they meant. Here's the scary part. A drifting model doesn't crash. It keeps producing confident predictions, smiling politely while being increasingly wrong. Traditional IT monitoring is the server up, is the API responding, sees nothing amiss. It's like a watchman checking that the lights are on while the accountant inside slowly loses his eyesight. So what does good monitoring look like? 3 layers: technical health, latency, uptime, errors. Statistical health: are input distributions shifting? Are prediction patterns changing? And business health: are approval rates, complaint volumes, or loss rates moving unexpectedly? Mature teams track all 3 on dashboards with defined thresholds and named owners. Your audit questions almost write themselves. What metrics are monitored? What thresholds trigger action? Who receives the alert? And what did they do last time one fired? Ask for the last 3 months of alerts. Silence in the alert log means either a perfect model or a blind monitor. Guess which is more common. So monitoring has told us the model is drifting. Now what? This lesson covers retraining, how organizations refresh their models, and more importantly for you, whether that process is governed or chaotic. There are broadly 2 philosophies. Scheduled retraining, refresh the model every quarter, like servicing a car every 10,000 kilometers, regardless of how it sounds. And trigger-based retraining, refresh when monitoring crosses a threshold, like taking the car in when the engine light blinks. Mature organizations combine both, a regular cycle plus emergency triggers for sudden drift, major world events, or new regulations. Now here's where auditors earn their fee. Ask the simple question: what exactly triggers a retrain, and is it written down? I once asked a team this and got the answer: when the business complains loudly enough. That's not a trigger, that's a smoke alarm made of customers. And retraining itself is a risky operation, because a retrained model is a new model. It needs the full treatment, fresh validation, bias testing, documentation, approval, and controlled deployment. There's a temptation to treat retraining as routine maintenance and skip the ceremony. Resist accepting that. Some of the worst incidents happen when a routine refresh quietly learns something toxic from recent data. Remember, the model retrains on the world, and sometimes the world has been misbehaving. One more subtlety: the data feeding the retrain may now include the model's own past decisions. A lending model that rejected certain groups never sees whether they'd have repaid, so the bias feeds itself. That's called a feedback loop, and we'll meet it again in the bias chapters. Governed refresh or improvised patching? Find out which one you're auditing. Every life cycle ends, and today we talk about the stage almost everyone forgets: decommissioning. How does an AI model retire? It sounds administrative, but I promise you, ungoverned model retirement is a quiet risk factory, and the AAIA syllabus explicitly covers it. First question: when should a model retire? Clear criteria should exist. Performance has degraded beyond repair. The business process it served has changed. A better model has replaced it. Regulations have shifted, or the vendor behind it has vanished. Without criteria, organizations accumulate zombie models, systems nobody owns, nobody monitors, but which still make decisions somewhere. I once found a pricing model still running 18 months after the team believed it was switched off. It kept quoting prices from a discontinued strategy. Nobody noticed because nobody was looking. Second, the process. Retirement isn't pulling a plug. Downstream systems consuming the model's outputs must be identified and migrated. Remember our dependency chains from Chapter 2? Access must be revoked, infrastructure released, and here's the big one, records preserved. Regulators can ask questions years later. Why was this customer denied in 2024? You need the model version, its training data lineage, and its decision logs archived for the retention period, even though the model itself is gone. Think of it like a hospital retaining patient files long after the doctor retires. And third, knowledge transfer. The people who built the model move on. If their understanding leaves with them, the archived model becomes an unreadable fossil. So, close every lifecycle audit with this question. Show me a model you retired and walk me through how. Their answer tells you whether the whole lifecycle is truly governed or just the glamorous parts.